Okay, let us start. Now, several of you asked questions about this derivation, so I'll go over some of the fine points. First of all, let me go over why do we take this thickness distance v delta t? Okay? How many people do not understand that? Well, okay. So, I'm imagining the following thing. I'm sitting next to the wall. I have a watch, and I have a chronometer, okay? I start looking at t equals 0, and I keep watch for a time interval delta t. And I'm going to count the number of molecules that come and hit the wall. Okay? Say between 0 and 5 seconds. Now, some of them that were at time t equals 0, already very close to the wall, will soon come and hit. Some of them very far, running with velocity vx, after time delta t will come from here to here, and will not reach the wall. So what is the farthest that they are when t was equal to 0 and I started counting? That will allow them to reach the wall within delta t. Well, within delta t, they are running a distance vx delta t. So all molecules that are nearer to the wall than this critical distance vx delta t will make it. Anybody who is farther away than vx delta t, okay, they will move a distance vx delta t and come here and not the wall. That's the idea. Okay? Then, to count how many of them there are, well, if they are within this distance, then they are within a volume A times Vh times delta T. I know the density of the gas, I suppose. The density is N over V. So, N over V times A, Vx delta T, that's the number of molecules. Then comes the next question, which I explained at the end of the lecture, and many of you asked question about that. You are confused. You see, N over V, the density, times AVx delta T, is the number of molecules who are within this volume. But what am I interested in is, okay, this is the volume within which if a molecule is moving towards the wall, it will get to the wall. But not every molecule within this volume is moving towards the wall. Some of them are moving away from the wall. Okay? And the fact that this is a random gas, there are no forces that, other than the wall itself, that tell the guys to move, turn around and you all move towards this wall because I want you to hit them. There is no such force. Okay? It's all random in a gas. Therefore, the likelihood, or what percentage of the molecules within this volume, or any volume in the gas, are moving to the right is 50%. I know what is confusing you because you say that it seems like half of them are moving to the right with the same velocity vx, let's say 3 meters per second, and the other half are moving to the left with minus vx, with 3 meters per second. Of course, that is not the case. What I'm saying is, for every molecule that happens to have an x component of velocity vx equals 3 meters per second, there are as many molecules with that velocity as with minus that velocity. I'm not saying that some of them, all of them are moving with the same Vx. I haven't got there yet. Okay? I just considered one molecule moving to the right with velocity Vx, say 3 meters per second. Okay? In the end, very soon, I will replace this velocity with the average velocity. of all these molecules, because of course they are not all moving with the same velocity. They have velocity components in the x direction, let's say, that can be 1, 1.5, 1.27, 3.5, etc. But as many molecules with 3.5 meters per second are there as there are with minus 3.5. And a certain number with plus 1, as many with minus 1. Why? Because there is symmetry between left and right. Okay? So for any velocity component in the x direction plus Vx, there are going to be as many molecules moving to the right as to the left. The question of how many molecules have 3 meters per second x component, and how many 5 and how many 7, plus or minus, okay, that I'm not discussing. That is more complicated. That depends on other properties of the gas. What I'm saying is, if I think of one molecule whose velocity to the right is 3 meters per second, within any volume of the gas, there are as many molecules, not all of them, but as many who have plus 3 meters per second as there are minus 3 per second. Okay? Therefore, I put a 1/2. Then that gives me the number of molecules whose x velocity, x component of velocity, to the right happens to be Vx equals, let's say, 3 meters per second. But to the right. Okay? That's why I have the 1/2. So it's 1/2 of those guys with x component absolute value 3 meters per second are to the right and 1/2 to the left. That's true for any velocity. Is that clear? Yes? Now let us continue. There were some very nice questions, by the way. One person asked, okay, he understands why it is half, but is it always the case if there are some other forces? So not really an ideal gas, but there is a force that favors one direction. Is it still 50-50? The answer is no. For example, our atmosphere. Our atmosphere is an ideal gas, but there is an external force on it because our atmosphere is near the surface of the Earth. Okay? Which means if I choose the x direction to be height, perpendicular direction, and if my wall is here, the surface, there will be more molecules closer here than very high up. The density of the atmosphere is larger at low altitude, and as you go higher and higher up, the density is less. So the left and right, or top and bottom part of the box is not the same. Why? Because there's an external force that defines a direction. It says it's better for you. You have lower potential energy if you move down. Okay? Is this clear? So what I'm assuming here is external forces are negligible. There is no preferred direction in this box. And then you get the 1/2. Another good question was, why do we use delta T and why we don't use a derivative? Wouldn't a derivative give me a better idea of the force? This is right, but the thing is, I didn't say anything about delta T being small or large. I'm assuming it's a small interval, and everything that I grab about the gas will be true if delta T is actually dt, is very small. Okay? The argument is just an estimate of what is the average force. And you will see that in the end it will disappear. The delta T itself will disappear. It is buried under the force. The force is delta P over delta T. If it's dP over dt or larger or smaller time intervals, it won't matter. Is this clear? Okay. Now I can go on. Next point is total force applied by wall on gas Okay? F total equals the number of molecules that collide with the wall within delta T, which is this. Times the momentum they exchanged. The momentum given to each molecule by the wall is minus 2m. That's the force given by the wall on the molecule. It went from plus mv to minus mv, right? Okay. If I concentrate on what force the wall applied on the gas, it is directed in the minus x direction. That's why I put back the minus sign. All right? That is the total momentum change of all the molecules in the gas that collide with the wall during time delta t. And you divide this delta p by delta t to get the force. Okay? If you go back a few pages in my previous lecture, we already got the momentum change of one molecule. It was this thing, minus 2 mvx over delta t. So it is a 1 over delta t here to make it a force. Okay? And the total number is proportional to delta t because of this argument that you want the guys who are able to get to the wall during this time delta t. It's proportional to delta t, Vx delta t. Okay? So the first thing I get here is that the delta t is cancelled. And what do I get now? Well, one other thing also cancels. The tools cancel. This is nice. They came for different reasons, but they cancel. Okay? And what I have here is that the total force equals A M Vx square. Efendim? Unuttuğum için. Hemen koyayım. En önemli şey. Çok teşekkürler hatırlattınız. Okay. I forgot here, as your friend pointed out, I forgot to put in, and let me put it over here. Okay. Right? Now, I started my discussion with one molecule and I said, well, it has some velocity Vx and maybe it is 3 meters per second. But now I am talking about trillions of molecules, and their x component of velocity is not, of course, going to be all the same. It's not all going to be 3 meters per second or whatever. Okay? The net result will depend, I have learned from this argument, on Vx squared, but Vx is not the same for everybody. Okay? So I have here average Vx squared. So these two triangular brackets means you have to take the average of something. Okay? Is this clear? My result depends on Vx squared, but not every molecule has the same Vx. They have some random distribution of directions, and some of them may go faster than others in total or in the x direction. So if I calculate the total force on all these trillions of molecules of gas applied by the wall, what it contains must be the average velocity square. Is this clear? Yes? Any questions on this? So all the previous arguments I assumed concentrating only on molecules, those molecules in the gas which all had 3 meters per second. So those come from this Vx delta T and they have this force, etc. But there are other molecules which have a different Vx and they will come from this Vx delta T and they exchange NV to NVx of momentum. Okay? So every type of molecule, every subclass of molecule whose velocity in the x direction is Vx will contribute to this force in proportion to its Vx squared. And there are many different Vx's, so the net result will be whatever the average Vx squared is. Okay? Now I see on the right hand side that there is an area. And I can write this equation as follows. Force, total force per unit area equals m Vx square average n over V. So the total force does not appear. Instead, the total force over area appears. Now let me think about this. Does that make sense? You see, if I have a small box here, like this big, okay, then I will deal with this much area. And what I'm counting is all the molecules who hit this area. And the number of such molecules is, of course, proportional to the area. If I have now a bigger box, there will be more molecules in the box. So as the area increases, the force increases. The bigger the area, the bigger the total force. What's important must be, the physical property of the gas is, how much force is applied by the wall on the gas or by the gas on the wall per centimeter square. That's an intrinsic property of the gas. Okay? The same kind of gas, the same kind of velocities will give the same force per area, because that depends on only the average velocity squared, and it depends on the density. So these are properties of the gas. They are not properties of how big your box is. Okay? So the relevant physical property of the box, of the gas in the box, is force per unit area. Force increases in direct proportion to area because it's the force per centimeter square that remains the same. Okay? So I better give it a name. So this is what I mean by emergence. Remember, when you go to larger systems, new concepts appear. Here I have found, by thinking, starting from microscopic laws, starting from Newton's laws, when I think about lots of molecules in a gas, I find that the area appears in the total force in such a way that force per area depends on V square, on the property of the gas. Okay? So force per area is a new concept that is obviously going to be important in this simple formula. Force per area has no meaning for a single molecule, because area is the property of the container that you put the gas into. All right? But area by itself is not important even for the gas, nor total force. It's force per area that will always appear. So let's give it a name. So now a new concept is emerging. Okay? And that new concept, we give it a name, pressure, basınç. It's just a word which means force per unit area. Now, notice that I didn't say force per unit area perpendicular to the x direction. Because who cares whether I call that direction x direction or y direction or z direction or something else? right? The whole derivation would work in exactly the same way if the wall was this way, or that way, or this way, or this way. For any direction of the wall, I can talk about the component of momentum perpendicular to that surface. I can say, well, that's the only thing that will change if I put the surface there. No forces in the other directions. So the whole argument, everything else will be true, except the name of the direction perpendicular to my wall will not be, it will be something else. That is not something that matters physically. Okay? Which means this formula for pressure is the same also for the bottom and top and left and right and all of the surfaces of my box. Furthermore, it is the same for any imaginary surface, because I can say that here, somewhere within my box, not one of the walls, deep inside the box, let me imagine a mathematical plane going through there. If I now think, if in this imagined plane I put a real physical piece of metal so that it applies a normal force, it doesn't pass the gas molecules from one side to the other, it would then, I imagine, if I put something here, it would apply a force. And all my arguments would be true for any imagined surface in any direction within the gas, right? It is therefore telling me, due to the velocities in the gas, mvx square, okay, there is going to be a force on any area. What I applied, what I derived here with the minus sign is the force that the wall or any surface that you insert in the gas will apply on the gas, because it's not passing the molecules from one side to the other. This is totally independent of the direction of the wall. It doesn't even have to be a real wall. You can imagine any surface in any orientation within the gas. If you put a real metal wall there, rigid wall, would exert this force. Now, by Newton's third law, whatever a rigid wall exerts as a force on the gas exerts equal and opposite force on the wall, right? So, a wall reflects the molecules back into the gas, so it's pushing them into the gas. Therefore, by Newton's third law, the molecules, by colliding on the walls of the gas, is pushing the wall out. Okay? And this is true, this formula is true for all walls, provided instead of Vx squared, you put the velocity square in the direction perpendicular to that wall. Real or imaginary, anywhere within the gas. Is this clear? Now, if you think of this whole argument, think of it also as an example of the scientific method, because what we have done is we have dissected, analyzed the thinking into simple bits, and then we have chosen specific examples. Let the velocity be in the x direction, let it be 3 meters per second, this and that. And then finally we ask, does this argument change if it's not the x direction? If the velocity is not 3 meters per second, but 5 meters per second? And the answer is no. Does it change if the wall is not real, but I imagine some plane in the gas? No, it doesn't change. So I start with simple arguments, which seem, if you think about them, all individually very simple, and then I keep building abstractions on it, and arrive at a result, which is a property of the gas, independent of the shape, direction, etc. of the walls. Okay? And then a new concept has emerged, which I call pressure. Another new concept has emerged, number per unit volume. Remember, here, the volume of the gas by itself should not be important. It is the same type of gas as long as the more volume I add, the more number of particles I also add, so that the number of particles per centimeter cube is the same. And that is N over V, that's the density. That's also an emergent quantity, it refers to a macroscopic system. Okay? So let me also identify that. Okay, this is pressure. And this is density. Okay, pressure, force per area, so what are its units? Newtons per meter square, and that is given a name for this unit, it's called the Pascal. In honor of a 17th century philosopher and mathematician and scientist, Blaise Pascal, who didn't define this unit, of course, but he was one of the first people who made experiments about pressure. Okay? And N over V, number density. Our unit for that is, of course, what? The meter minus 3, 1 over meters cubed. The number has no units. Okay? Now, here's what we got finally. We had pressure equals some property of the gas, the average NVX squared, times N over V. Other than that thing, which is a property of the gas, which is the same for the same gas, what this tells me is that the pressure of a gas is proportional to its density. And this is something that people knew. When? Well, from the 16th and 17th centuries on, pressure is obviously something you can measure, because you can, for example, take a gas, put it in a container, make the top of the container movable, piston, put a weight on it, and let it come to a balance. When it comes to a balance, it means the force of uplifting by the gas equals the downward push that you apply on the piston, because it's not being accelerated. So that's a way to measure forces exerted by gases divided by area. That will give you the pressure. Okay? And density, of course, is something that you can measure, because you can just weigh the gas, find its mass per unit volume. Okay? That should be just proportional to the number of atoms in the gas. So, but this thing that we derive is a prediction from Newton's second law and just mechanics and energy conservation, etc., that the pressure of a gas must be proportional to its density for the same type of gas. Okay? And this was known, or immediately verified, empirically. Now, what is this NVX squared? First of all, we see that it is sort of like kinetic energy. First thing I notice, well, there's an X here, but what I call X and what I call Y and what I call Z is not important. So I expect that Vx average square must be equal to the average of Vy square and the average of Vz square. And if you remember that V square equals Vx square plus Vy square plus Vz square, we have n Vx square is just 1 over 3 of mv square. Not for one molecule, of course. For one molecule, Vx, Vy, Vz can be different numbers. But on the average, there is no reason for the speed square of motion in the x direction for the average of trillions of molecules is any different from speed in the y direction square, or z, right? The sum of Vx square plus Vy square plus Vz square is total V square. So each of them, on the average, is 1/3 of the average total V square. Okay? I can write it like that. I have 1/3 instead of 1/2. If I have 1/2, if I have 1/2, that's kinetic energy. So I have here the following result. The pressure equals 2/3 times the average kinetic energy of the molecules times the number of molecules per unit volume. And that allows me to identify another important quantity here. This thing I'll call U, the energy density. Why? Well, this is simple. I'm saying if I have n molecules per meter cubed, and each of these n molecules has 1/2 mv square average kinetic energy, the average kinetic energy of the molecules times their number is the total kinetic energy of all the molecules in 1 meter cubed. So it's the density of energy, kinetic energy per unit volume. Is this clear? Any questions about this? So I can now express my law in a very simple way. Pressure equals 2/3 the energy density. Which just says the physical reason for the gas to push out on the surfaces to apply pressure is because the gas is jumping around, all the molecules are moving with kinetic energy in all directions. And the more kinetic energy per unit volume there is, the more pressure. Okay? So the unit of energy density is joules per meter cubed, which is the same thing as newtons per meter square. Of course, it's the same units as pressure. Pressure and energy density have the same units. Pressure counts because molecules have kinetic energy, and the actual value of pressure is just 2/3 times the average kinetic energy per unit volume of this gas motion. Is this clear? Now, many experiments were done, and it was shown that pressure indeed is proportional to some property of the gas having to do with this average kinetic energy times density N over V. Okay, let me cut it short here. Pressure is a positive quantity. All gases push outwards, positive quantity. Of course, the number is a positive quantity, number per unit volume. This is also positive. And the kinetic energy, because of the V square, the average kinetic energy is also. Everything here is positive, right? As numbers. And V squared, the average kinetic energy of the molecules in a gas, is, of course, a property of that gas. Not all gases have the same average kinetic energy. Now, from early times when people started making experiments, physicists and chemists started putting gases in containers and making experiments, they were aware, of course, that gases sometimes feel hot, sometimes colder. So there was an empirical, practical notion of hotness, coldness, temperature. Okay? And people didn't know what temperature really meant. But they were able to define a scale for it. Because there is something called phase transitions. Water and other substances are sometimes liquid, sometimes gas, sometimes solid. So they knew that under certain conditions, water is ice, and then if you heat ice, what does heat mean? In those days, as far as they understood, if you put it next to something hot, okay, it melted into water, and then if you keep heating it, eventually it boils. So they said that, let me define a scale, a gradation of colder to hotter, hot and cold. And one of the definitions that we still use was the centigrade scale, which said, I'll call the hotness, coldness, temperature of water when it just freezes is 0. And when it evaporates to steam, when it boils, I'll call that 100. And I'll do careful experiments measuring how much water melts, how much other water, etc. to grade this into equal degrees of hotness, coldness. This is totally empirical, without really understanding what is the meaning of temperature, okay? But temperature was a known property, of course. As soon as you do physics and chemistry, you don't have to do science. You are aware that some days you feel hot and some days you feel cold, right? There is some such a thing. Okay. And then when you experiment with gases, naturally, temperature was first an empirical quantity, but when you experiment with gases, you ask questions like, how does temperature and pressure of a gas relate? So they knew that some things felt hot, some things felt cold. They also knew that if you put a hot thing together with a cold thing, they eventually come to the same hotness. First the hot thing warms and the other one cools, etc. So the result of that is they knew about temperature. And then you can do the following experiment. Pressure, temperature. You know how to put weights and measure the pressure with a gas under a piston. Okay? Of course, you keep the same gas, which means okay? For constant density gas, if you make sure that the density is constant and measure temperature versus pressure, they noticed that as you increase the temperature of the gas, so did the pressure increased, and the proportionality was N over V. So with a different N over V, you get straight lines. And then, if you now put the centigrade scale here, you notice that in the experiments, as you increase higher temperature, higher pressure, and it's a straight line, okay? And the experiments, of course, were done in those days. Only over here, at temperatures between, maybe -10 and +200 or so, okay? And they get a straight line. You get a different straight line purely from experiment for different different densities, N over V, but for each constant density gas, okay, you get pressure times temperature. Sorry, pressure with respect to temperature is a straight line. Okay? And then, once you notice the straight line, and you realize that pressure has to be a positive quantity, you extrapolate the straight line into lower and lower temperatures, where in those days, the technology didn't exist really to cool and do experiments. But if you extrapolate the straight line, you found that this straight line, one straight line at one density comes down to -273 degrees centigrade. Then the natural question that the scientists asked is, what if I do the experiment in a different density, another straight line, where does that extrapolate? And the fantastic result was that all different density gases, pressure is always proportional to temperature. I don't know what temperature is, but it's proportional. And the extrapolation of the graph for different experiments at different densities, all of them extrapolate to the same point. And that point was at -273 degrees centigrade. So you can define a new temperature scale. T degrees Kelvin is T degrees centigrade plus 273. If you make it that way, this new scale is positive all the way because it is 0, the Kelvin temperature is 0, where pressure is 0. Okay, and pressure cannot be less than 0. So this is called the absolute temperature scale. Now let us compare this with what we derived from Newton's laws. The proportionality between pressure and density is 1/3 mv squared. In the experiments, pressure is proportional to something called temperature and density. For the same density, it's proportional to temperature. So this thing must be temperature. It's a proportionality constant, so it must be proportional to temperature. And the scale of temperature in some units depends on how you define the degree, which is 1/100 of between ice and steam. So that's one operational definition. That defines the proportionality constant K, which is called Boltzmann's constant. And this T here must have the property that this T scale must go to 0 at the point where pressure goes to 0. Experimentally, I know there is such a point, as I just showed. It's the absolute 0 of temperature. So if you put the temperature in Kelvin degrees, and you work out from experiment, measure pressure, measure density, etc. What is the proportionality constant? K, okay? You get its value. 1.4 times 10 to the minus 16 ergs per degree, or 1.6 times 10 to the minus 23 joules per degree. I won't write it now because it's in your book. But do you all understand, first, that we understand the ideal gas mode pressure is proportional to average kinetic energy times density. Second, experiments empirically show that pressure is proportional to temperature, degree of hotness, times density. Therefore, this degree of hotness and average kinetic energy must be the same thing. So the physical meaning of our psychological feeling of hotness and coldness is the average kinetic energy of the gas. That's temperature. This we understand from Newton's laws. Okay? Okay. Finish for today. This is the end of mechanics. On Wednesday, we will begin electromagnetism, and soon we will distribute a second part of the book that covers electricity, magnetism, and quantum mechanics.